Okay, so welcome to the second session of today's talks. Our next speaker is Professor Mike Giles at the University of Oxford, and he's going to be speaking on optimization of MLMC on FPGAs. So thank you very much for accepting the invitation, and please take it away. Thank you.
Thank you very much, RJ, and sorry I can't be with you in person for this workshop. So this presentation is on work that Irina Haas did as her master's dissertation last year. And it's looking at the mathematics of how to optimize multi-level Monte Carlo as applied to field-programmable gate arrays. So a particular new computing technology. So I'll say a little bit about FPGAs and, well, yeah, this is the whole outline of the talk, but let me move straight on to the FPGAs. They've actually been around many years, I mean, at least 30, 40 years, but they've not really broken through, I would say, into the mainstream of scientific computing, except for one or two niche applications. But the key thing about them is they're very energy efficient, and in particular, very efficient in that you can customize how many bits you use to represent the numbers that you're working with in your calculation, and particularly efficient if you can use fixed point arithmetic rather than floating point arithmetic. I'll say more about that in a couple of slides' time. And so I think by exploiting multi-level Monte Carlo, I think there's the potential to make them really useful in computational finance. So that's the motivation for this work. So setting the scene, if we're looking at just a simple one-dimensional SDE, stochastic differential equation of this form, where we have a drift term a dt, and then the stochastic term b dw. So dw is the increment of Brownian motion, normally distributed variance of delta t, or dt. Then we approximate that most simply with the Euler-Maruyama method. Okay, so this is our discrete algorithm for advancing the approximate state of the path from one time step to the next. And for the purposes of this talk, let's suppose we're using uniform time steps of size h. Okay. We're then, in simple applications, interested in the expected value of some payoff function, capital P, which depends on the state of the path at some final time, capital T. Okay. And simple Monte Carlo estimate for that, we would simply do n independent path simulations using different random numbers for each of the time steps, and then take an equally weighted average of all capital N simulations. And if those samples have a variance of V and a cost per sample of C, then we can achieve an epsilon root mean square accuracy with a number of samples that's approximately equal to epsilon to the -2 times V. And the corresponding cost of that is the number of samples times C, the cost of each sample. Okay, so that's standard Monte Carlo. Moving towards multi-level, let's first start with a two-level setup. So suppose we want to estimate some quantity P1, but it's much cheaper to simulate some other quantity P0, which is roughly equal to P1. Well, in that case, we can use this trivial identity that the expected value of P1 is the expected value of P0 plus the expected difference. And then, rather than using Monte Carlo to estimate the left-hand side, we instead use Monte Carlo to independently estimate each of the two right-hand sides. And so we use the following estimator, where we have N0 samples for estimating the expected value of P0, but N1 samples for estimating the expected value of the difference. And the key is, because the difference is small, and we're using the same stochastic inputs for both P1 and P0, the variance of the difference will be small, and therefore we won't need a very large N1 to accurately estimate the expected difference. So if we then optimize the number of samples, N0 and N1, to achieve a given epsilon root mean square accuracy again, what we end up finding is that the cost behaves like this: epsilon to minus 2 times the square of the sum of the square root of variance times cost. Okay, so V0, C0 there are the variance and cost of P0. V1, C1 are the variance and cost of the difference, P1 minus P0. Going from two-level, there's a very natural generalization to multi-level, where we have a whole sequence of levels, which in the context of approximating an SDE would correspond to progressively increasing the number of time steps. So we're getting more and more accurate approximation of the path evolution. And so now we can say that the expected value of P on the finest level of resolution is this telescoping sum of expected corrections, delta P, okay, with P minus 1 being defined to be 0. So that first delta P0 is basically just P0. And so we use the multi-level estimator, where we have a sum over levels, and on each level we use NL samples to estimate the expected value of delta PL. And each level of simulation is using independent random numbers. The total cost then, it generalizes, choosing the optimal number of samples on each level to epsilon to the minus 2 times the square of this sum over level of the square root of variance times the cost. Okay, so that's all nice and standard. In the context of the FPGA, so this is really a critical slide to look at, what we are doing is using nested multi-level, in which we nest the two-level treatment inside the standard multi-level. So what we have here is a sum over levels, which corresponds to the number of time steps. So say that we have the number of time steps being 2 to the power little l. So we have the sort of outer multi-level structure corresponding to the time stepping. And then at each level, we want to compute the expected value of delta P. And we split that into two pieces. We split it into a delta P tilde, which corresponds to a low accuracy fixed point calculation being performed really efficiently on the FPGA. And then that second piece, the difference between the sort of proper, correct delta P and this low accuracy approximation, delta P tilde. Okay. So in that correction term, the delta P will be computed on a CPU, the delta P tilde will be computed on the FPGA, but they'll be both computed using the same random input. So again, the whole, the sort of two-level, multi-level structure works for this inner sampling. And so then, if you analyze, the optimal number of samples for all levels and for the split between the FPGA and the correction, then overall the total cost behaves like epsilon to minus 2. And again, we have a sum, but now on each level, we have a sum of these two square root pieces. Okay. And so here, C tilde is the cost of evaluating delta P tilde. So that's a very low cost. And V tilde is the variance of the difference between the true delta P and the approximate delta P. And what we hope is that that variance is small compared to the regular VL. Okay, so on a level L, then, we can rearrange the sum of those two square root terms in the following form. So on the right-hand side, that square root of VL CL, that's our standard multi-level cost on level L. And then we have the sum of these other two terms. So what we want to achieve is CL tilde being much smaller than CL and VL tilde being much smaller than VL. Okay, so that's a low FPGA cost compared to the CPU cost, and a small variance for the correction relative to the usual VL variance. And so what that shows us is that we have a trade-off here. We want a small VL tilde, we want a small CL tilde. So getting more accuracy would naturally come with a higher cost. And so we're looking for a sort of sweet spot in the middle here, which gives us a low variance and a low cost. Now, I say that we're aiming for a trade-off in accuracy. What is it that we're actually adjusting here? Well, there are two things for us to adjust. One is the accuracy in generating the normal random variables, that we're going to start from uniform random variables and need to convert those into normal random variables. We're going to look at cheap ways of doing that. And then the other thing is, in implementing it on the FPGA, we're going to have the freedom to choose how many bits to use to represent all of the variables in the calculation. And so that's another part of the optimization. So let's start with the approximate random variables. So we're going to be generating uniform random variables, and that can be done very efficiently. So that's not a concern in terms of overall cost. And then we're going to have a transform to convert them into normal random numbers. And usually the way that we would do this would be to use the inverse of the normal CDF function. So think of it in those terms. With the FPGA, we won't use all of the bits of the random variable U, we'll just use the leading D bits. Okay, so that gives us our U tilde, our approximate uniform random number. And we're going to feed that into an approximate conversion into normal random variables. So we want to, really minimize the cost of this transformation. And so thinking about that, there are three good options. One option is, if we have D bits, we can just take a piecewise constant approximation of the inverse transform on 2 to the D intervals, each of size 2 to the minus D. So that's a simple direct lookup. We have an integer random number with D bits, and we use that to index into a lookup table. What's not clear to me currently is what the cost of implementing that would be on an FPGA, the extent to which that would be a viable solution. I think actually for doing work on CPUs where you could hold the lookup table in level 1 cache, I think doing similar work in that context with half precision computing on the CPU, I think that may actually be a viable way of going. For a second approach, which is one that's been used before on FPGAs, and I think is also the basis of what Intel uses for its vectorized implementation, is to use a piecewise linear approximation on intervals that get smaller as you approach u equals 0 and u equals 1, the two extremes of the interval where there's a singularity in the inverse mapping. So that's that's a very interesting method and has worked well in the past. Another method, which I think could potentially be the best of the three, is to take the D bits, split them into two sets of D over 2 bits, one of which you take as a sign bit, use a lookup table for the D over 2 bits. So now, that's a much smaller lookup table. And so what that's going to give you are two approximate normal random numbers, Z1 and Z2. And if we design that so that each of those has a variance of a half, then returning the sum of Z1 plus Z2 gives an approximate normal with a variance of 1. And you can optimize those lookup table values to get a surprisingly good output from this two variable method. The advantage of this method over the first method is the size of the lookup table. Much smaller lookup table. You have two lookups, one addition, but I think this may be a good technique for the FPGA. So here on this slide, I'm plotting the mean square error in this approximate random number generation. So this is comparing the approximate normal values to the true normal values, varying the number of input bits. The solid line at the bottom, that's the best you can do. That's the full lookup table, which may or may not be a feasible approach for the FPGA. The dotted and the dashed lines, they correspond to the two variable method. The original one is when you sort of pre-calculate the lookup table values based on the average value of the inverse mapping. And then the optimized version is when you then get to work to optimize those values to get the minimum discrepancy with the true values after you go through this two variable process. And then the dyadic shows the effect of that method. So it works well with a small number of input bits, not so well for the higher bits because of the approximation error implied in the linear fit to the inverse function. So anyway, a number of interesting different approaches there. Let's now look at doing the fixed point arithmetic. So in floating point, what we're used to using on CPUs, we represent the floating point number in this way, that we have a sign bit, so we have a plus or minus 1 times m times 2 to the power e. So m here is a number that lies between 1 and 2, and then e is an integer exponent. Okay, and so in floating point calculations, m and e are both variables. They're part of how you represent a floating point number. In fixed point numbers, we have a fixed exponent. Okay, so if we have d bits being used to represent a variable, not including the sign bit, then that variable is represented in this form: -1 to the s, n times 2 to the e minus d. So n here is an integer, going from 0 up to 2 to the d minus 1. Okay. So the exponent is fixed. We have to choose the exponent to be big enough to hold the largest number that we need to represent in the application. And then after we've fixed the exponent, it's the number of bits d, which is going to control the precision of the variable, how accurately it's represented and involved in all of the subsequent calculations. Okay. So roughly speaking, if you're adding together two numbers, then the cost is roughly proportional to the sum or the average of the number of bits being used to represent each of them. And then when you take the output and round it to the precision that you have for C, the rounding error is bounded by this quantity based on the exponent of C and the number of bits being used to represent C. And then similarly, if you multiply two numbers, the cost of multiplying is roughly proportional to the product of the number of bits involved in both A and B. If you think back to how, as a child, you did long multiplication, you can see why the cost scales as the product of the number of bits, whereas for addition, it scales like the sum of the number of bits. We're actually going to bound that product as being 1/2 of the average of the squared values. It's convenient for us to have costs where we don't have, we have sums of terms that depend only on one or other of the inputs. That'll pop up when we talk about the optimization later on. And again, the rounding error is bound by the same magnitude. Okay, so we have an idea now about the cost of implementing the FPGA algorithm. What we now want to think about is what are the errors that are introduced on the FPGA by doing it in low precision? Well, to leading order, the error in our output quantity P, we can look at as a linear perturbation analysis. We can say that if at one point in the calculation, we're calculating some variable x, and we have an error delta x, then the consequential error for the final output delta p is just the p dx times delta x, to first order. So I'm calling that x bar I. This is actually the notation that people use in the area of algorithmic automatic differentiation. So this is linked to doing backpropagation in machine learning, where you can very efficiently calculate the sensitivity of your final output quantity to a whole set of input parameters, or in this case, a whole set of rounding errors at different points in the calculation. And so with a very efficient sort of pre-calculation, we can get representative values for these X bar sensitivities. Now, from path to path, those sensitivities will vary and the errors will vary, okay, because of all the random inputs, the paths are all completely different to each other. We get contributions from each operation in the path calculation. If we want to be conservative, what we can say is that the root mean square error in the output is the sum of the root mean square errors occurred as a result of each one of the rounding errors. So this is allowing for the possibility that there may be complete dependency between some of the errors. And then we can bound that by this sum over each of the operations, the square root of the expected x bar squared times that 2 to the EI minus DI minus 1. On the other hand, if we model the errors as being statistically independent, and if the rounding error is modeled as being uniformly distributed over that interval, then we have the variance of the sum is equal to the sum of the variances. And so then we have the variance of delta p is bounded by this sum over I of the expected square of the sensitivities. And then we have this expression for the variance of delta x. Okay, so we have these two models for how we can look at the error analysis. We then tested this on simple geometric Brownian motion. So here, this shows how the multi-level simulation sort of looks like on level L, where we're iterating through the time steps with the old path value on the course level being updated every second time step of the fine iteration. So we're generating our approximate normal random variables. We've got a number of simple operations. I've laid this out instruction by instruction because we're going to look at each one of these variables. So mul1, sum1, mul2, etc. And for each one of those variables, we're going to decide what is the optimal number of bits to use to represent it. Okay. And then at the bottom there, we get the delta p. So that's really the approximate delta p when we're doing this on the FPGA. Okay. So this comes out of a simulation where we've simulated the effects of an FPGA by using a toolbox which exists in MATLAB. So it's a very handy toolbox for doing algorithm development in advance of actually implementing on an FPGA. The solid line here with the sort of stars on it, that's the actual observed variance, varying as we increase the word length, as we increase the number of bits being used for all of the variables. So in this figure, we're using the same number of bits for all of the variables. And what we're interested to see is which of the two error bounds is more realistic. We have the independent bound, which is the dashed one, and then the more pessimistic bound that allows for the possible dependency between the errors is the dot dash bound. And what we're seeing here is that actually the independent bound is a more accurate representation of the error. So this is for the level 0 simulation. This is for the level 4 simulation. So really what we concluded from these experiments is that using that independent bound, treating each of the rounding errors as being statistically independent, although that isn't sort of mathematically justified, in practice, that is the more accurate error bound. So for the purposes of optimization, we're going to use that error bound to give us a prediction for the variance of our results. And remember, this is actually the variance of the difference between the FPGA approximate simulation and the true simulation, which will be on the CPU. Okay, so on the basis of that, then, we have this error model for V tilde, the variance of the difference between CPU and FPGA. We're going to use the same number of bits for the path at all stages in its evolution. and for all instances of these other variables at each time step in the simulation. And so that ends up giving us the sum over 7 terms. There are 7 different variables for which we are optimizing their widths. Then we count up all the additions and multiplications which each variable is involved with. And what that gives us is a quadratic cost model. So dk, being the number of bits we're using for a variable k, the quadratic bit comes from the multiplications, the linear bit comes from the additions. Okay. This is ignoring the error and cost due to the approximate normal random numbers, because we don't currently know how to model that cost. Okay, so what we're doing here is looking at how do we optimize the number of bits being used to represent each of the variables. So our goal now is, given that cost model and that variance model, we want to minimize this quantity at the top, the sum of the 2 square roots. Okay, and we're arbitrarily fixing CL, our CPU cost, to be 10 to the 4. So that's 10 to the 4 relative to the C tilde cost being given at the bottom there, with A and M being the number of additions and multiplications, and dk being the number of bits for variable k. So this is a somewhat arbitrary choice of picking 10 to the 4. We think that that's realistic, but this is where we need real experimentation on an FPGA to see whether that number is actually sensible. Anyway, to minimize, we differentiate with respect to the number of bits, dk, in each of the variables. And I forgot to note on the previous slide, the key thing with that cost and variance model is it's a sum of terms, each of which depends only on 1 dk. So when we differentiate, we get this equation dv tilde dk plus lambda dc tilde dk. We get sort of independent equations for each variable k. And they're linked all through having the same lambda, which controls the trade-off between cost and variance. And so what we can do is, for each lambda, it's a simple 1D Newton iteration to get the optimal dk for each one of the k's. And then that gives us a cost as a function of lambda. And then we do an optimization on lambda to minimize the cost, or minimize that quantity at the top, the sum of the 2 square roots. Okay. So this gives us, that sum of the 2 square roots. If that's less than 1, then we're winning compared to standard multi-level, all being done on the CPU. We've got 2 curves here. One corresponds to using the same number of bits for all variables. The other one uses optimized number of bits. So this is a level 0 calculation, and it turns out there the optimization of the word length, the bits, doesn't make a huge difference. By the time you go up to level 8, then we are seeing more benefits from optimizing the number of bits with different variables using different numbers of bits. And in fact, on this slide, we see, varying with level from 0 up to 10, we see how the number of bits for the different variables changes. So things to highlight here, I guess, the solid line with the sort of stars at the top, that's the number of bits needed for the path calculation itself, to hold the value of the path, S. So that's the one that most requires the accuracy. Because as you have more and more time steps, if you have rounding errors on each time step, you get a greater accumulation of error. And so that's why as you go to finer time levels, we need more precision in holding S. Whereas starting at level 0, 10 bits is perfectly sufficient. Okay. What else to note here? That thick line is the random number generator. So that's saying how many bits we need in the random number generation to create the normal random variables if we want to not incur an error that then starts to swamp the error due to the round-off error. Okay, so that gives you an idea of just how much accuracy we'll need in the random number generation. What you can also see is that for some of the variables, I mean, right at the bottom there are two variables, con1 and con2. So they're a couple of constants. They correspond to things like sigma times h, so the volatility times the time step, or times the square root of the time step. That actually we don't need very many bits for those. So ranging from only 5 bits being needed on level 0 up to what's that, 8 or 9 bits being needed on the very finest level. So there's quite a variation in the accuracy required. Okay, so this then gives us, the optimal value of this sum of the two square root terms. And so you see how that varies with level. You see how it varies between using a uniform number of bits on all variables compared to using the optimized number of bits. So really, at this point, we've taken the mathematical analysis and optimization as far as we can, before actually looking to do an FPGA implementation. So taking the overall cost, again, it's in this form with this sum over levels. The reduction factor for the geometric Brownian motion test case is approximately a factor 15 reduction with uniform bit widths, using the same number of bits for all variables. And with the optimized bit widths, then factor 24. So a useful additional benefit from optimizing the bit widths. But this does ignore currently the cost of generating the random numbers, because I'm not sure what a good model would be for that. But I don't think that is going to be a costly process. So I'm fairly confident in that. Okay. So future work. We're planning to have a collaboration with University of Warwick. So Heb, who's there with you in the auditorium, and also a colleague, Gihan Mudalij, who used to work with me here in Oxford. The three of us have put in a research proposal to try to get funding to get a postdoc to do the implementation of this. These field programmable gate arrays traditionally have been really painful to program, but these days there's a high-level C++ software platform that's been developed by AMD, which hopefully will make this much less of a challenge than it used to be. So we have to then, assess these, the costs and benefits of these different techniques of converting uniform random variables into normals. We have to assess how accurate our cost model is for the fixed point arithmetic. We may need to prove that, need to implement the CPU part of the algorithm and do the full multi-level coupling and to get the overall cost savings. And then the other thing I want to do, and in fact I have some master students working on currently, is to do corresponding development of methods using half precision floating point arithmetic on both CPUs and GPUs. So we have a sort of fair head-to-head comparison really between FPGAs, GPUs, and CPUs, and see which of these wins out overall. Ends up either being most cost-effective or most energy efficient. Those are two slightly different metrics for success. And then moving on to other SDEs in the future. That would be the aim, assuming this is all successful. So thank you very much. Here are some references for the work. So Irina's got a paper in Monte Carlo methods and applications that's just come out a couple of months ago. So thank you very much.
Thank you for the talk. Thank you so much again, Mike. Do we have some questions from the floor?
Hi, Mike. Thanks a lot for the interesting talk. The plot on 25 was really surprising to me, so I kind of want to maybe take a chance to study it more and ask you a question about it. So the fact that it's different rates, depending if it's uniform or optimized, I guess it's a direct result of 24, but the plot on 24. But I was wondering, where do you see the biggest bang for your buck in terms of rather than optimizing individual operations, maybe optimizing different types of operations, or accumulation, having variables having a certain number of, rather than every operation having a different bit count, maybe having a bit count for accumulation operators, a bit count for multiplication operation, a bit count for addition. So having sort of buckets of such optimization rather than every individual operation.
Okay, so yeah, so this really comes from this slide. So oh yes, I forgot to note this. There's a dashed line there, very near the top, which is the uniform one. So that's the number of bits on the different levels when all the variables have the same number of bits on that level. So what it shows is that if you go with the uniform strategy, you pretty much have to go at the accuracy of whichever needs it most, which in this case is the path variable S. So the fact that the optimized one has a lower overall cost is because some of the variables don't need that very high accuracy. It also explains why the cost savings here get poorer as we go to the finer levels, because you're needing more accuracy for some of the variables. So it's a possibility that we would decide that we only want to use the FPGA for the first, I don't know, 6 levels. And after that, we just do everything on the CPU. Particularly if we're doing something, like the Milstein approximation, where most of the cost anyway is on the course levels. I mean, in some ways, looking at the figure on page 24, slide 24, I'm surprised we don't get more savings from doing the optimization, because a lot of variables have significantly reduced cost. I guess the issue is that the S variable, if I go back to here, the S variable is involved in multiplications and additions, and it's involved in quite a lot of the calculations, so a significant proportion of the overall operations involves S, and so it's the S accuracy really does drive the cost to a significant extent.
I'll say thanks for Abdul here. This is Rob. I'm gonna follow it up. So my question was in the context where we used it for more linear algebra type applications in UQ with mixed precision. We based it on this analysis like Nick Hayam and so on, where they sort of, again, like Abdul said, put it in blocks and say which blocks should be done at that accuracy and which block should be that accuracy. And then we were even able to do some blocks at quarter precision. So that was my first part. And the second part was the random number generation. I think it was actually you that introduced it to us when we used it for SDs before with these discrete approximations. Wouldn't it be also valuable to go down the discrete route where you can then have decision trees to not do sampling at all anymore on the coarsest levels? If you know what I mean. Discrete approximations of Gaussian random variables where you simply take whatever, a 5-point discrete random variable. What we used for this stuff we did with the Met Office. I don't know if you remember.
I don't remember now, but how did that differ to doing the piecewise constant approximation, where it's just a direct lookup table?
Yeah, it's related, but it's more it's matching the moments rather than just doing the adic. But maybe that's exactly what you mean there. And then you have a tree. You have maybe just 5 states, and you can go down the tree like explicitly. You don't need to sample anymore. I think it was you that introduced it to us. We did it with Ike and Tony Shadlow.
Oh, so
I'll talk to you separately because this will take. I'll talk to you separately. I think it'll take it offline. Yeah.
Okay. Yeah.
Too far.
Yes, maybe that came from.
But the first question: what about using rounding error analysis, clear rounding error analysis, like this sort of mixed precision rounding error analysis?
I mean, this is very much similar to the sort of rounding error analysis that Nick did. Nick didn't tend to like just doing the sort of linear analysis like this. So he tended to be a little bit more conservative in the way that he treated things. But our experience has been that doing this linearized analysis and then modeling them as being statistically independent is actually a good model for the way things behave in practice. So although you can't rigorously justify it, it is in practice a more accurate model that is therefore more meaningful in terms of designing an optimization for the bit sizes.
Okay, so we're at time now. So let's thank Mike again. Thank you very much for your talk.
Okay, thank you.